So for electron structure, we know the Bohr model doesn't work anymore because it's not as simple as just electrons orbiting in rings. They actually have many different shells and subshells, and this is kind of a map of them because it's really too hard to draw like a Bohr model. So instead of doing a Bohr model, we use this map instead. Each one of these guys, we'll do a little lesson here, each one of these guys is a subshell. The 1 represents the shell. The S's, P's, D's, and F's represent subshells. So in the first shell, I've got this here. The second shell, I have 2 regions, S and P. And the P is a little higher in energy. There's an energy axis here. The third shell, I have an S, a P, and a D. But notice they're not filling up in order anymore. The 3D is way up here. So they fill up according to this axis, energy. But they don't fill up distance from the nucleus anymore. Once we get to a certain level, they just fill up by whichever one has a lower energy, and sometimes the farther out ones have less energy than these interior ones. But nonetheless, 3S, 3P, 3D, that's in the third shell, 4S, 4P, 4D, and there's a 4F. Those subshells are in the fourth shell, fourth ring, if you want to think about the Bohr model that way. 5S, 5P, 5D, 5F, that is the fifth shell of the electron cloud. And then 6S, 6P, and 7S. That's all that we really have there. There is a 7P too, but it's not on this chart. The way they fill up is by low to high energy, and this is how the periodic table is arranged. So we see all these regions, and there's 4 chunks to the periodic table. So we get the 1S, and then we go to the next row. 2S, 2P, 3S, 3P. They fill up in this order. 4S, and now we're into the D block. We notice that this is an interior now. This is in the fourth shell, this subshell. 3D is now in the third shell, but it has higher energy, so it fills up after. So we need to call it a different thing, 3D. 4S, 3D, 4P. And all of these, we're going to subtract 1 from whatever row that we're in. So if we're in the fourth shell, we're going to go 1 more lower to fill up those. So 4S, 3D, 4P, 5S, 4D, 5P, 6S, there's a break in the periodic table here. It jumps down here to 4F, 5D, 6P, 7S, 5F, 6D, 7P. They fill up in the order that they are in the periodic table. The electrons go in these subshells. Remember, this is just a map. This isn't like the real periodic table. Elements aren't in these orbitals. They have electrons in these subshells, in their outermost electrons. So this is just a map. It's a guide. Write electron configurations for the following neutral atoms. Boron is going to be pretty easy here. 1s2, 2s2, 2p1. Boron only has 5 electrons. So there they are. 2 in the 1s, 2 of them are in the 2s subshell, and 1 of them is in the 2p subshell. Vanadium has a lot more. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and it stops at 3d3. It has 3 electrons in that subshell. It's kind of its location on the periodic table, but remember we just say those are the electrons that vanadium has in those subshells. It's not in the 3d subshell. Its highest energy electrons are. Flerovium, well, that's the bottom of the periodic table, and that's a huge one. So let's pause here. So I've got part of it written here. 3d10, I'll pick up where we left off. 4p6, 5s2, and then we go inside a shell, 4d10, and then back out 5p6. Next row we go 6s2, and this is where there's a break in the periodic table, 4f14. 5d10, it goes back up, and then back out to 6p6. And then the last shell, the last row of the periodic table, 7th shell, 7s2. Now the F block goes down to F5F14, 6d10, and 7p2. For those of you unable to find, I probably should have started with this, flerovium on the periodic table, that is element 114. It might not be named on the periodic table you're looking at. I suppose I should have started with that. It's at the very bottom. Now this also says, write their noble gas configurations. Okay? The noble gas configuration is a shortcut. So it takes the noble gas that it's closest to and simplifies this, because let's be honest, that's kind of a pain in the butt to write all that, especially for the big ones. So boron has a similar electron configuration to helium plus some extras. So we find helium there and we kind of block it off. Vanadium has a similar electron configuration to argon. So this first part here is argon. We block that off. Flerovium has an electron configuration, that's a huge one, very similar to radon. So radon goes all the way up to 6p6. And once we kind of isolate those noble gases there and kind of where they are, boron, we would just say, okay, boron is like helium. And then we continue with the outer shell, 2s2, 2p1. Vanadium, we said, was like argon. So those in brackets there represent argon, and then we go with the outermost shell, the highest energy ones, because the D's are in there too, that's not the outer shell, 3d3. And then vanadium is similar to radon, plus some extras, 7s2, 5f14, 3d, sorry, that's not right. So 5f14, then we go back up to 6d10, that's the one, and then 7p2. So there's the noble gas configurations and the electron configurations. Even to something like draw orbital diagrams for the following: sodium, phosphorus, and chlorine. Alright, these get a little messier. So, sodium. The electron configuration for sodium, 1s2, 2s2, 2p6, 3s1. We're going to draw that then. I'm going to do that with lines here instead. 1s, I put 2 electrons. 2s has 2 electrons. Now 2p has 3 orbitals that are degenerate. So we put the electrons in up, 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 down, down, down. They're all equal energy, so we put them there. And then 3s has 1 electron in it. Phosphorus. We go again. 1s, it has 2 electrons. 2s, 2 electrons. 2p6 is next. Up, 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 down, down, down. They're all equal energy. 3s, those are full as well. And phosphorus, its highest energy electrons are in the 3p subshell. There are 3 of them. Up, up, up. So we spread them out that way. Chlorine. Alright. We go again. 1s has 2 electrons. 2s, 2 electrons. 2p, 3 degenerate orbitals. Up, up, up. Down, down, down. 3s has 2 electrons. 3p. Chlorine, its highest electrons are in the 3p. There's 5 of them in the 3p subshell. Up, up, up. Down, down. So we can get electron configurations and orbital diagrams for these. How many core electrons do the elements have, and how many valence electrons? Well, if we remember here, valence electrons mean the outermost electrons. That does not mean the highest energy. That means the outermost. Outermost is these numbers here. So it's the 1, 2, 2, 3, 3. What's the highest number in this set? It's 3. So 3 is my outermost shell, the third shell. So we have the third shell there. Those are the valence electrons. So 3s2, 3p5. Chlorine has 7 valence electrons. Same thing with phosphorus. It's the third shell is my valence shell. 3s2, 3p3. That has 5 valence electrons. That means the rest of those are core electrons. At this break, and it's not always a clean break, Anything that's not the highest number there is core electrons. They both have the same number of core electrons. That's 10. They both have 10 core electrons. Core electrons are in the lower shells. The valence electrons are in the outer shell. If we could go back even, I don't know if this will let me go back, so let's just go forward. If we had something such as, come on. Okay. If we had something, I'll just do the noble gas configuration that we did for flerovium. For radon, 7s2, 5f14, 6d10. This is element Fl, flerovium, which is may or may not be on your periodic table. 7p, what was it? 2. Okay. The highest energy shells here, the valence shell, this is 7, 5, 6, and 7. It's the 7 ones. Those are valence, and those are valence. They're in the 7th shell, 7th energy level. Those are the highest energy ones. 5f and 6d are in the interior of the atom. This is 2 layers inside. This is 1 layer inside. Those are technically core electrons. Now they fill up after the 7s, but the 7s electrons and the 7p, those are in the valence shell. So valence electrons are always in the s's and the p's. Okay, write the electron configuration for the following ions. So let's get started here. Sulfur -2 is different from sulfur because it has 2 extra electrons. So let's see how that affects the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p. Now sulfur normally stops here at 3p4. But sulfur has 2 extra electrons, sulfide, so we put them there and we fill it up, 3p6. Now argon is neutral. Let's take a look here. 1s2, 2s2, 2p6, 3s2, 3p6. Calcium plus 2 ion. 1s2, 2s2, 2p6, 3s2, 3p6, and then calcium has a 4s2, has 2 electrons in the 4s subshell, but the calcium 2 plus ion lost those electrons. They don't exist there. So now we lost that. The interesting thing with this one is, let's kind of plant some seeds here. We lost a shell. That 4th shell is actually gone. And now all of these have the same electron configuration. That is called isoelectric, the same electron configuration. They're all identical in terms of their electron arrangement, but there is one difference between them. So let's kind of highlight this now because this will be a big point going forward. They still have different number of protons. That will affect their properties. Sulfur has 16, argon has 18, and calcium has 20. And those protons are positive. That will affect how they interact with and pull those electrons. That will affect size and other properties, reactivity, all sorts of things. So we do need to keep that in mind. Even though their electron configurations are the same, this is kind of what we mean by being like the noble gases. They're isoelectric with the noble gases. Their properties are still different because of the protons attracting those electrons differently in different sizes. So keep that in your mind going forward, and those kind of wrap up electron configurations.